Hello everyone, my name is Minuk Ma. Today I'm going to review a paper titled Meta-Reinforcement Learning of Structured Exploration Strategies. Meta-Reinforcement Learning of Structured Exploration Strategies. So we have meta-learning, reinforcement learning, and associated exploration problem. This is table of content. So at first, what is meta-learning? I assume that everybody knows the basics of reinforcement learning, so I'm not going to explain about it. But what is meta-learning? This paper is built on top of a framework called Model-Agnostic Meta-Learning. There are many meta-learning frameworks. For example, learning to learn by gradient descent is about learning the step sizes while training process to achieve faster convergence rate than Atom Optimizer for some situations. The second component of this paper is policies with latent space. With these two, we get model-agnostic exploration with structured noise. What's it all about? Efficient exploration is crucial for RL agent success. Efficient exploration makes RL agent learn faster. Then the point is, how can we make it explore? There are many basic strategies that you already know, including epsilon greedy, or parameter space noise, or maintaining state visitation counts for all states, and make the agent go to unexplored state, something like that. But this paper is about learn to explore from related tasks. So MESN is fusion of MEMO, Model-Agnostic Meta-Learning, or Meta-Learning for fast adaptation, plus input space hidden variable. So meta-learning is about learn to learn. You can think of pre-training as a type of meta-learning. So you have a single model, a classification model for ImageNet dataset, but that model can be transferred to solve other tasks like detection, segmentation, face recognition, something like that. So when we have better representation, we can achieve faster learning of new tasks. In this paper, they consider this situation. First of all, we assume there are many tasks, many related tasks, and assume there is a distribution over those tasks, like maybe detection, classification, segmentation, recognition, something like that. And assume that we can sample a task from the distribution. Oh, now we got task 7. So now we have a model theta and task 7. And train model on task 7 just a few iterations. And we can get a high-performing model theta prime, which is specified for task 7. The point here is a few iterations. The representation theta is very general that it can be fast adapted to many other related tasks. Many virtually arbitrary tasks in this distribution. So it says, I can evolve to any model, and it says, now I'm good at task 7. So what kind of situation is this in practice? What is this distribution over tasks? In this paper, they specifically considered these kind of situations. The left figure and the right figure. So this is an MDP where the initial block positions can be in this area, and the goal position, the red box, can be here in any of this position. Now MDP is a tuple of 5 quantities, right? S, A, R, P, and gamma. The block position means state, and the goals is related to the reward. If any of these 5 quantities change, then it means it's different MDP. But we all know that these are very similar. They're all related. In this case, it's the same. The goal position is along this line. As I said, this paper is about learn to explore from related tasks. So if our meta-learner is very successful, I think this agent will do this. It will go to the right and sweep this parabola, because it knows from past experiences that the goal position was here, 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 right? All the goal positions was along this line. Then it knows that, oh, maybe given a new environment, it's highly probable that the new goal position is also along this parabola. Now let me explain a mathematical formulation. So consider a model F that maps observation X to output A. And assume that each task can be formalized in this way, with 4 quantities: loss function, the initial state, the transition, and horizon. When the horizon is 1, it's supervised learning, just like classification. In that case, there's no transition probabilities. But in reinforcement learning, usually H is not 1, and transition probability is complex. We consider a distribution over tasks PT that we want our model to be able to adapt to under this problem setup. Now, let me explain the conceptual problem setting and the overall algorithm. Note that this is still background 1. So the goal of this paper is to make something like stem cell in biology. In biology, stem cells can differentiate to many other types of cells, like muscle cells, blood cells, nerve cells, whatever. The ability is called pluripotent. It's very potential and general. What we want is the same. We want a very general feature that can be used to learn other tasks. So given a new task T, with only a few iteration or few adaptation, you can think of it as few-shot learning. The performance gets high for that task. How do you do this? So first, we prepare randomly initialized model theta, our pluripotent theta, and assume there is a distribution of our task. We sample n tasks from the distribution, okay? N tasks. For adapt the model theta to each task to get n adapted models, theta t1, theta t2, up to theta tn. For example, theta t1 is for detection, theta t2 is for segmentation, theta tn is for facial recognition. We want 5, measure performance or loss for each task, like this. 6, our objective is to minimize the sum of all losses and update theta via using gradient descent. Note that we don't update these ones, we update this one, because our goal is to make a very potential theta that can adapt it to solve other tasks very fast, and we want the adapted models perform well for each task. This is a detailed algorithm for model-agnostic meta-learning. As I said, we assume there is a distribution over tasks, PT, and alpha and beta, which are step size hyperparameters for adaptation, and the real update for pluripotent theta. As I said, we first randomly initialize theta. We have a loop, sample batch of tasks, ti, from the distribution of tasks. So we have n tasks. And for each task, we adapt the model to each task. How do we adapt that? Gradient descent. We evaluate the loss function and take gradient with respect to theta with k samples, k examples for each task, and compute the adaptive parameters with gradient descent to get theta I prime. We'll get n of these adaptive parameters. And after doing this for all n tasks, we want to measure the performance. So we equipped the adapted theta and measure the performances with the adaptive models on each task, which is LTI. What we want to do is to minimize the sum of all these loss values to update the real theta, the pluripotent theta. For reinforcement learning, it's just the same, except that we don't have k examples a priori, but we are going to collect or sample some data for each task. Well, now we finally arrive background 2, policies with latent space. So the latent state is used for exploration. Typical stochastic policies parameterize action distributions using an action distribution pi that is independent for each time step, like epsilon greedy. We decide action and just put randomness into the action space. We roll a dice. If we get 1, we just choose random action again. If we get 2, 3, 4, 5, or 6, we just stick to the original plan. However, this representation has no notion of temporally coherent randomness throughout the trajectory, since the noise is added independently at each time step. This greatly limits its exploratory power, since the policy essentially changes its mind about what it wants to explore at every time step. To incorporate temporally coherent exploration behavior and allow the policy to model more complex time-correlated stochastic processes, we can condition the policy on per-episode random variables drawn from a learned latent distribution, like Gaussian. Since the latent variables are sampled only once per episode, they provide temporally coherent stochasticity. Intuitively, the policy decides only once what it'll try for that episode and then sticks to this plan. Furthermore, since the random sample is provided as an input, a neural network, nonlinear neural net, policy can transform this distribution into arbitrarily complex distribution. The point of MAML, this is the framework which this paper builds on top of, learns a model that can easily evolve. But Mason, this paper, learns a model that can easily use the random variable for exploration. The goal of Mason is to meta-train theta so that they can make use of the latent variables to perform coherent exploration on a new task and adapt as fast as possible. As I said, from related past experiences, the agent may decide to go to the right and sweep through a parabola, for ideal case, of course. And it's about meta-training. Meta-training involves optimizing the initial theta, which are all shared for all tasks, and the per task initial variational parameters, mu0, sigma 0, mu1, sigma 1, blah, blah, blah. So these are associated with Gaussian distribution, and we're going to take a sample. We're going to choose some samples, C, random variable and then concatenate the state and z to construct a new state, stochastic state. Now finally, let me explain how Meson works. It says, from past experiences, I learned how to use random variables to explore, ha ha ha. Okay, so the goal is to make a model theta that can explore in a new environment well with latent variable z. Prepare a randomly initialized model, theta, and sample n tasks. Each task has associated hidden variables distribution. At first, for all tasks, the distribution is normalized to Gaussian distribution with mean of 0 and variance of standard deviation of 1. For each task, run k episodes with concatenation of s, z as input, as I said. For adapt theta, mu I, sigma I for each task to get an adapted set of variables. So this is the adaptation step. Then we'll get theta I prime and mu I prime, sigma I prime up to n. Now equip those n adapted models and measure the performance of each task. We want the models work well for each task. So update the pluripotent model theta and variables mu and sigma to maximize the sum of the performance. This is the detailed algorithm. Now the experiments. There are 3 environments which this paper considered. One is object manipulation with a robotic gripper, pushing various colored blocks to the red goal square. And the right figure here shows the distribution of blocks in the orange region and the goals in the blue region across the task distribution, indicating task diversity. Here, another environment is locomotion with a wheeled robot navigating to the goal, depicted by the green sphere. And the goal state, as I said, is along this parabola. Another environment is the same with this, but it's not bi-wheel robot, it's legged locomotion with quadruped. This is the experimental results. So for all environments, the proposed Meson showed the state-of-the-art performance compared to other baseline methods. For example, when they only use latent space, hidden variable, in the input space but does not use meta-learning, the performance is lower, or simple TRPO performs lower. And this plot shows how the agent explored. So we can see that Meson shows wider search spaces, and we can see that in one episode it does not go back because the exploration strategy is temporally coherent, while for random case it's rather spherically radial because it's fully random. For other parabola environment, it's the same. Meson shows wider search space than the baselines. This wider trajectory distribution suggests that structure noise is being used. Thank you.